Welcome back to this video on calculus. We're talking about derivatives, and this is the second part of a video explaining exactly what a derivative is, reasons for which I explained in part 1. So in this we're going to talk about we're going to sort of pick up from where we left in the previous video and then go more in depth into the calculations that behind sort of finding out what a derivative really is. So before that, I just thought we'd go ahead and review what we did in the previous video and start on this review page where we actually ended in that previous video. So let's go ahead and just start here just to recap. So rates we calculate using our slope formula are averages. We did a couple of these calculations in the previous video, and it does not have to reflect what happens at each instant of time. And we saw examples of this in the previous video as well. And we sort of saw that the slope formula is more of an overall rate of change calculator. It does not actually tell you what happens at each instant. So that's what we finalized in that video. And now the question I left you with was, can we calculate rates of change at each instant of time? So in other words, instead of just taking the overall rate of change that we get with slope formula, can we actually find what the rate of change is at each instant of time? So for example, let's take the car example we talked about. If you went 300 kilometers in those 5 hours, can we calculate how fast you went at each instant? There's something we can use for that. Well, let's answer that in this video. But before we go ahead and answer that, I'm going to change this question slightly, and you'll see why in a bit. So I'm going to change it to, can we calculate the slope of a graph at a point? And really, this is the same thing, because the slope of a graph at a point is essentially the same thing as an instantaneous rate of change. You can see it graphically, and we'll look at this as well. And I'm doing it this way because this is how textbooks do it, so it'll help you if you're studying this in class. It'll help you understand it, and also because it gives us a more mathematical representation of what happens, and that kind of helps visualize some of the things you might visualize some of the calculations you might do. So, and also because a lot of the problem solving you'll have to do relies on your understanding of what the slope of a graph of a point means, I'm gonna go this way. Okay, so I hope this helps you, and yeah, let's keep going. So let's just go ahead and try that out right now. Can we calculate the slope of a graph at a point? So I've listed the slope formula here for you for your reference, and why don't you go ahead and just try this out. Calculate the slope at the point x is equal to -4, which is right about here. So why don't you just try that out right now, and just a little word of advice, don't be intimidated by your results. Just do it. So okay, let's just go ahead and do it together now. So m equals f of x, and notice this is slightly different from what we usually write of y minus y1, but really it's the same thing. F of x and y are the same thing I've explained in a previous video, and it's just different ways of writing the same thing. But f of x is used more commonly in stuff relating to calculus, so you should probably get used to seeing f of x. So that aside, f of x minus f of x1 is minus x over x1, which is just going to be f of x, which is f of -4, which is, and notice it's x squared, so we don't really need the graph to figure out what that's going to be. So x squared is -4 squared, which is going to be 16, minus f of x1, which is again -4, so that's just going to be 16 minus 16 over, and x is going to be -4 minus -4, again because x1 is also for -4. And you might see where we're going with this, but let's just take it on anyways. So that becomes 16 minus 16 is 0. -4 minus -4 is just -4 plus 4, which is also 0. And this is our final answer for the slope. Now this is a little bit of a problem, right? Because as we know, we can't divide by 0. Therefore this leaves us in a bit of where we're a bit stuck here. So what does this mean? Does it mean we can't calculate the rate of change at a point? Well, you're in luck, because actually, well, that's not the end. There's a little bit more we can do. It's just that we need to lay out that the approach of using slope formula with just one x coordinate with one point is not going to work for finding the slope at a point. That's just one thing we need to make clear here. But there is another way to do it, and we're going to take a look at that in just a second. So before we go there, here's some key vocab you need to know. So the secant line. A secant line is a line that intersects a graph at 2 points. This is something you might know from geometry, but it's a good recap if you forgot. So a secant line is a line that intersects a graph at 2 points. Now a tangent line is a graph that intersects the line that intersects a graph at exactly 1 point. So how do these two lines relate with calculus? Well, here's how. I'll show you in just a bit. But before, let's go ahead and have a little visualization of what they are, and maybe that'll tell you a little bit about how they will relate to what we're planning to do. So this is just an arbitrary curve I drew, and here's 2 points, and this is what a secant line would look like. Now on the same curve, here's another point, and this is what the tangent line would look like. Notice the tangent line goes through only 1 point, while the secant line intersects at 2 points. Now the tangent line intersects the graph at only 1 point. Let's just remember that. So if the tangent line intersects the graph at only 1 point, that must mean, right, that the slope of the graph at that point is the slope of the tangent line. So, and that also makes sense if you just take a look at it visually. Just if it intersects at that 1 point, it does give an indication that the graph slope would look like that, right? It makes sense. Just visually and just intuitively, that makes sense. So let's make that assumption. The slope of the tangent line represents the slope of the graph at a point, which is what we are looking to solve, right? We're looking to find the slope of a graph at a point, and that's what the tangent line does for us. If you take the slope of the tangent line, you can find the slope at a point. Okay, so with that information, let's go further. Now coming back to the same example here, I've drawn what the tangent line would look like at x equals -4, but as we know, we can't use just slope formula and x equals -4 to calculate that slope. So here's what we're gonna do. What we can't do, as we know, is use just f of x equals -4 to calculate the slope. What we can do, however, is use 2 points to calculate a slope, right? Because that's what slope formula is all about. You can use 2 points to calculate the slope. So let's try that out. So I use these 2 points and I calculate the slope of the line, and yeah, it looks nothing like the tangent line, right? It's this line's going this way, that line's going that way. They look nothing similar. Now what happens if I choose another point that's closer to x equals -4? Like, take a look at that. Now suddenly it looks a little bit closer. Obviously it's still a bad approximation of what the tangent line might look like, but it's getting closer. As our x value approaches closer and closer to this -4x value, our tangent line is our secant line. This is a secant line, in case you didn't figure that out, because it intersects the graph at 2 points. Our secant line is starting to resemble the tangent line even more. I hope you get that feel from this video. The secant line is starting to look more and more like the tangent line as we get closer. It's still not perfect, but it's getting closer. Let's pick another point even closer. As you can see, it's getting even closer. This is, again, it's still not perfect, but it's getting really close now. So it's getting pretty close to the tangent line. And if I could pick even more points. I could pick this point, x equals -3, x equals -2. I could pick those points, and even up to x equals -3.99999. And eventually I would get pretty close to what the tangent line is. So ringing any bells? All right, let's move on then. And yeah, look, as I'm getting even closer, the closer I get. So let's make some notes. Notice here, as the points get closer and closer together, the secant line begins to resemble the tangent line even closer. That's what we made the inference, right? As we made border point closer and closer, the secant line began to start to look a lot like the tangent line. Or, in other words, the slope of the secant line, denoted by m subscore sec, is getting closer to the slope of the tangent line. They're getting closer and closer to each other. Okay, so for the secant line to equal the tangent line, the difference between the 2 points will need to equal 0, right? Because that way the secant line would be the tangent line, and that way their slopes would naturally be the same because they're the same line. However, we know just based on our calculations that we cannot use direct slope formula to calculate that slope. So here's what we can do, however. To emulate this, we'll need to use a limit. Now, how does the limit work here? Well, let's take a look here. So here is the slope of the secant line. Or for example, if you just took a curve, the slope between any 2 points would just be the slope of the secant line. That would be this, just f of x blah blah blah. That's how you do it. But what if you wanted to make a tangent line? What if you wanted to bring the distance between those 2 points to 0? What if you wanted to find the slope of the tangent line? Then you'd have to bring the distance between those 2 points really close to 0. We can't make it 0 because then we get 0 over 0 as our slope, but we can get it really close to 0, and for that we use a limit. So let's take a look at what the slope of the tangent line would be. The limit as x approaches x1 of f of x minus f of x1 over x minus x1. So basically what we're doing is we're using a limit to bring the distance between those points really close to 0, so that we can have a secant line that has a slope that's really close to the slope of the tangent line, so close that it doesn't even matter anymore. They're pretty much the same thing. So that's where the limit also plays in. This is where now you can see this is where calculus is really starting to come into play. Until now it was mostly algebra. Now we're starting bringing calculus into it. Okay, so let's move on. So this is what we call the definition of the derivative. The limit as x approaches x1 of f of x minus f of x1 over x minus x1. This is something you should memorize. It's really helpful it's really helpful in general if you memorize this. Okay, so the formula for the slope, the formula for the slope of the tangent line is what we call the definition of the derivative. So that's right. Let's try and lay that out there. So the slope formula, the slope of the tangent line. This is the definition of a derivative. So you'll see this a lot in your prep books, in your notes, and even in your textbooks. A lot of what you'll see something like this as the definition of derivative. Now let's not forget what this is though. Let's not forget what this actually tells us. It can be used for calculating instantaneous rates of change, or the slope of slope at a point. The last thing I want to leave you with is another version of the definition of the derivative, and this version is something you'll probably see more often. It's often easier to work with than this definition we've derived here. It just is a little bit harder to see graphically, so I'm going to sort of derive it from the definition we've got right here. Derive. Okay, so let's go ahead and talk about that here. So first step, we're going to let x minus x1 equal h. Now one thing I want to make clear here is that x minus x1 is the difference between the 2 points. Between the 2 points or between the two x values. Okay, so that's one thing I want to lay out there. So now let's go ahead and plug this back into here. Now how do we do that? Now here it's obviously a direct substitution, but what about over here? How can we put this in here? Well, if you think about it, what are you really doing here? When you take the limit as x approaches x1, what are you actually doing? Well, you're bringing the distance between those 2 points really close to 0. And what's the difference? The distance between the 2 points, the difference between the 2 points is represented by h. So if we're bringing the distance or the difference between the 2 points close to 0, then we're also bringing h close to 0. Therefore, this will be the limit as h approaches 0 of, and the denominator is just going to be h because it's basic substitution. Now what about the numerator? What do we do with that? So we have x and x1. We can't have both of those in there just because the thing will no longer make sense. But what we're going to do is, because we have x, we have this extra x we want to get rid of. Now what we are going to do here is we're going to go ahead and try to substitute. We're going to rearrange this equation and then substitute it back so we can get rid of that x there. So here's what we're going to do. I'm going to do this in different color just for aesthetic pleasure. We're going to add x1 to both sides. I'm going to add x1 to both sides, and what does that turn out to be? These two will cancel out, and then what we're left with is x equals x1 plus h. And really this makes sense just intuitively as well, because if you take two numbers and find the difference between them and then add that difference onto the smaller number, you're going to get the bigger number. So take 6 and 4, for example. If you take the difference between 6 and 4 and you add that to 4, you're going to get 6, right? So that this makes sense. So here's what we're going to do. We're going to plug this back into here now. So here's how we're going to reword this. This would be f of x1 plus h minus f of x1 over h. And this is the second version of the definition of the derivative. Sorry, it's not perfectly clean, but you get the picture. So we have two definitions of the derivative now, and this should give you a pretty solid understanding of what the derivative is. And yeah, that brings us to the end of this video. I hope you found it helpful. Hope you learned something. Hope you now have a firm grasp of what a derivative is, what it means, what it tells you, and also how we got these definitions. So that being said, I'm gonna end right now. So please subscribe, watch more videos on my channel, and leave a comment. Any constructive feedback is always appreciated. I'd like to know how I'm doing. So yeah, thanks for watching. See you.